We, however, have examined this model in detail, and we had actually several papers on this subject. And we do have some interpretation for beta 0 and beta 1, and you can find them in some of our papers. But the interpretation is not quite as clean and convenient as the parameters for the exponential model. Okay, so this is the other common model. Now let us talk about, okay, we have these different models that people have contributed. So there are dozens and dozens of models. How do you know which one is a good model? And there are two ways you can compare models. Now this is actually a general problem. It's a problem in software reliability engineering. It's a problem anywhere in any empirical science where you have a model, and if you want to see which of the competing models are better. So for example, we have been working with vulnerabilities, and there again there's a question of modeling. So how do you compare models? Now one approach is use some kind of goodness of fit. There are several goodness of fit measures. That you can use, and basically at goodness of fit measures, so you have a hypothetical plot, and you have the real data, and you see how far those real data points are from your hypothesized model using some criteria, and that would be a goodness of fit measure. Other approach is to look at predictive capability. I think this is probably not a good piece of chalk. Let me try this one here. Predictive capability. So the idea is this: what do you need a model for? And basically you need a model. The main use of a model is to be able to predict. So you have some data, you fit that data in with a model, and then you make a prediction that by this time I would have detected most of the faults, or I would have, the failure intensity would have fallen below some pre-specified limit. So you want to make predictions. So the question is, how do you judge the prediction capability? So there are two measures that can be used, and this is how I will define those two measures. Let us say that we have data points, and data points are failure intensity at some point t sub I, and I is equal to 1 to some n. And let us say that total defects found, total defects, this is the actual number, by the end of testing is, let us say, D, and estimate of total defects at time t sub I, let us say that is d sub I. So this is the real number, and this is your estimation. So at some point, time t sub I, you make a prediction, and this is your prediction. Okay, how far is your prediction from the real number? You are of course not going to know as long as you are doing testing, but at the end, when you have all the data, you can evaluate the predictive capability of your method. So you can evaluate two things. You can evaluate the average error and let's call it AE. And so this is to take the average, and I'm sorry, that should be I equal to 1 to n minus 1. Prediction minus the real value, normalized by dividing it by the real value. So this is average error. So basically you calculate the error of prediction at every point in time and take the average. Now there's, you can talk about, sometimes you are not interested in, oh, I'm sorry. Here, let us assume that we are not interested in the sign of the error. We are only interested in knowing how far the result is from the real number. So you take the absolute value. However, sometimes you are interested in knowing on which side the error is occurring, because it is possible that a method would tend to overestimate or would tend to underestimate. You can calculate average bias. And for average bias, you will not take the absolute value, otherwise the expression looks the same. So you can take different models, and you can take a data set, use the data set to calculate, get the projections, and then you can make the projections as data is coming, and then eventually you can calculate average error and average bias, and then you can repeat it for all the models and see which model gives you the best average error or average bias. So this is what we did. We compared a number of reliability growth models. Two of them we have seen. So let me show you the plot that we got.
So Dr. Malaiya,
Yeah.
so when you compare the models, so do you consider number of parameters also?
Yeah, that is actually another issue, that this does not consider the number of parameters. Now, in this case, number of parameters is not that much a concern, but with fit, number of parameters is a concern. Because what happens if you have a model that uses more parameters, it will always be able to give you a better fit. Because if you have the more parameters you have, there are more things that you can tune to fit your data. So if you are measuring goodness of fit, then you should probably compare only models with the same number of parameters, because otherwise it is not a fair comparison when you talk about goodness of fit. However, here since we are looking at predictive capability, it is probably not a concern, because it's something that if you are adding any extra parameter just to get good fit, it will probably not help you in getting a good prediction, unless it happens to be a good model. So in this case, the number of parameters is probably not an issue. But number of parameters would be an issue if you are considering just only a goodness of fit, right?
is there any trade-off? Say there are two parameters on one model and the other have three parameters. And then a three-parameter model predict a bit better, but not that much better than two parameters model. But in that case, what complexity is matter, I think.
I guess if a model predicts better, even if it has more parameters, you probably would want to use that, because there's no disadvantage of using additional parameters.
You have to select
Because by looking at the predictive capability, so you are you're not doing anything artificial. Whereas if you are doing a goodness of fit, you can artificially put in some parameters which may not actually represent the actual behavior, but will help you make it fit. So in this case, we would not be doing anything artificial, because if you do anything artificial, then our predictive capability would not be good. So because we are doing predictive capability, so number of parameters, I think, is not a concern. But that's a good question. I think people have not thought about it. With goodness of fit, when people do, when you do chi-square goodness of fit, then that compensates for having additional number of parameters, because it takes into account what is the term? Degrees of freedom, which takes into account the number of parameters. But if you are doing R square, which is also a goodness of fit measure, R square could be a misleading measure, even though it happens to be a popular one, when you are using a large number of parameters. So this is what we found. So for software reliability growth models, we examined some model, and here are the average error values. So we looked at a, okay, this is plus 10 and minus 10, actually 10%. So for logarithmic model, we find this. There's a model called inverse polynomial. We found, so this is the logarithmic model that we had just talked about. This is the inverse polynomial. We have not talked about this model. This is a model that was proposed by Littlewood, a British researcher. And the exponential model goes like this. This is the exponential model. And then there is a power model. Which we have not talked about. And there is an S-shaped model. So this shows the average error, average bias. And so you can see that the logarithmic model it turns out to, these two models are compared. So these two are the best models. This also does an adequate job. And these two models are not quite that good. So this is a good model. So this is the model used. This is the model I would prefer to use for software reliability, unless there is another reason. This is also a popular one. And the reason this is not that popular is that it's kind of hard to use. Now, if you will plot average error, the plot for average error would look something like this. So let me show you a plot for average error.